All right, so if I'm ever doing a question like this, I'm first going to look to see if they're parallel, because that's easy to check. And well, yeah, really mostly because it's easy to check, right? Like, so if you look at this line 1, its vector, which I'm going to call V1, is 2, 4, -1, just the coefficients of t. In a similar way, for L2, the vector V2, the coefficients of the variable are -2, 3, and 2. So these vectors are definitely not parallel because these these lines are not parallel because these vectors are not multiples of each other. So we can definitely say not parallel. So then the way we answer the other 2 questions is they either have, so if they're not parallel, they either intersect or are skew. So we're going to check to see if they intersect, and if they don't, they're going to be skew. The way we check for intersection is typically, although really you can pick any 2. You set the x's and the y's equal to each other, or you can do the x's and the z's or the y's and the z's. And then you find an s and a t that work for that. And then, welcome, thank you. And then after we find the s and the t that work for those, we'll plug it into the z equation and see if it works for that. So I know we've done this before, but it's good to practice. So I'm going to set x1 equal to x2. So I have 1 plus 2t equal to 4 minus 2s. And then I'm also going to have, this is x1 equal to x2. And then y1 equal to y2 is going to give me -3 plus 4t equal to 1 plus 3s. And there isn't any one particular way of solving this. I would probably zoom in a little. I don't know. I guess I would probably find a 2t here. So I have, actually what I would probably do is the following. I would write this below here. I would actually multiply this by 2. So 2 plus 4t equals 8 minus 4s. And then I'm going to subtract this equation from it. -3 plus 4t equals 1 plus 3s. If we subtract those, 2 minus -3 is 5. 4t minus 4t is 0. 8 minus 1 is 7. -4s minus 3s is -7s. So subtracting the 7 there, I get -2 equal to -7s. So s is equal to +2 sevenths. Doesn't look very good, right? Oftentimes, if someone's thought about this problem ahead of time, they're probably going to be nice numbers. It doesn't mean it couldn't be, right? It could totally work. We still have to check. So I'm going to plug this back into either one of those equations and solve for t. Let's pick the first one. So I have 1 plus 2t equal to 4 minus 2 times 2 sevenths. So 2t equals, welcome, thank you. See, 4 minus 1 is 3 minus 4 sevenths. So 2t is equal to 21 minus 4, so 17 sevenths. So t is equal to 17 fourteenths. Okay, whoops, sorry, can't I see that? So we're going to check, does that work for z1 equal to z2? So z1 would be -1 minus t. -1 minus 17 fourteenths is -14 fourteenths minus 17 fourteenths, which is -31 fourteenths. And z2 is going to be 2 times s. Definitely not the same. So no, they don't intersect, which means they are skew. Cool. So now the follow-up. How far apart are these lines? Totally new question. So how far apart are L1 given by this equation? I suppose I could say the words. L1 given by x1 equal to 1 plus 2t, y1 equal to -3 plus 4t, z1 equal to -1 minus t, and L2 given by x2 equal to 4 minus 2s, y2 equal to 1 plus 3s, and z2 equal to 2s. Well, how far apart are these lines? For those of you just joining us, we've determined that these two lines are skew because they're definitely not parallel and they don't intersect. And now we're going to figure out how far apart they are. So skew lines, right? I'm always imagining like, literally I'm imagining like two pens lying in space where they're kind of like on top of each other and they're pointing in different directions. We can kind of draw that here. So if I draw like, let's draw the planes first. So here's one plane. There's another plane. And the thing about skew lines is that skew lines are, well, you can find planes that contain the skew lines that are parallel. As someone pointed out last class, you could also find planes that contain the skew lines that intersect. But the important observation here is there are planes parallel to each other that contain the skew lines. And we're essentially trying to find the distance between the two planes. So here's what we're going to do. We're going to draw this little picture first. And when I was noticing the other day, yeah, it's okay. So that's a right angle there. Right. So here are these two planes. They're parallel to each other, and we're trying to find the distance between these two planes. That's it. All right. So first off, we need to find the vector that gets us, that essentially is perpendicular to these planes. We're going to do this. The thing we, well, I don't say the thing we usually do, but we're going to do a similar sort of thing where we find this perpendicular vector, we find another vector like from one point to another point, and then we kind of use our either dot product or cross product to make to use a triangle. We're going to draw a triangle is what we're really going to do here. But let's find this normal vector first. Well, this normal vector is perpendicular to that line. It's also perpendicular to that line. So that means it's also perpendicular to the vector that goes in the direction of this line and the vector that goes in the direction of this line. So this n here must be perpendicular to both the vector for L1, which is 2, 4, -1, and the vector for L2, which is -2, 3, 2. All right, can anybody tell me, if you're trying to find a vector that's perpendicular to other vectors, what do you do? That's a good question. I have two vectors. I want to find a third vector that's perpendicular to both of them. That's a great time to use the cross product. The cross product will always give you a vector that's perpendicular to both of the vectors you're using. Now, I know it seems kind of weird because like this vector is in this plane and this vector is in this plane, but we could imagine them sitting right next to each other. And then their cross product is going to right-hand rule, point in the direction that's perpendicular to both of them. So we're going to find the cross product of these two vectors. So V1 cross V2, usual method, determinant of this 3 by 3 matrix. So let's see, V1 is 2, 4, -1. V2 is -2, 3, 2. And then we're going to get, so this is where it becomes good to like kind of just do the work. So we're going to get I times the determinant of 4, -1, 3, 2, minus J times the determinant of 2, -1, -2, 2, plus K times the determinant of 2, 4, -2, 3. So we're going to get, let's see, 8 minus -3 is 11i. 4 minus 2 is 2, but it's -2. And then 6 minus -8 is +14. So, or if you prefer, or this notation. So there's my vector n, perpendicular to both of these. So now let's go ahead and place this vector. Yeah, so we've got the lower plane here. And we need, yeah, do we need, sorry. Yeah, so we need a point in each plane. And there's some really easy points to find in each plane. I can find a point in each plane by letting T be anything you want. Specifically, I'm going to pick 0. And same thing for the second one. I'm going to let S equal 0. So that's the first one. So in my first plane up here, I'm going to have the point. So I'm going to draw this. Yeah. So I'm trying to make my drawing look good, which is always a challenge. Let's draw it up here. So my top plane here, I'm going to have the point 1, -3, -1. So there's my point 1, -3, -1. And in my bottom plane, I'm going to have the point 4, 1, 0. And I don't unfortunately know that these points are right over each other, right? They're almost definitely not. So what we're going to do is we're going to draw this vector n coming out of this point here. Yeah, we don't know how long it is. It's going to hit the plane right there. It's going to keep going. So there's our vector n. Right, you can make it longer or shorter by multiplying by it, right? It doesn't matter if it's not long enough to poke through the other plane, we can make it longer. And then we're going to draw the vector from this point P to this point S. And then we're going to draw the triangle. So look what we've got. We've got angle here, and I'm trying to find this length. We've definitely done this before. So I'm definitely run out of room before. I'm definitely gonna run out of room here. So let's keep going. Sorry, I'm trying not to run out of room, but it happens. So for that picture, we want to find this length. Do we want cosine or do we want sine? We definitely want cosine. Why am I using this angle and not that angle? Because I have these two vectors. I don't have this vector. So I definitely want to use this angle between the two vectors I have, and I want to use cosine of that angle. So cosine of theta is going to be the magnitude of this vector, which I'm going to call PS, divided by D, which we're going to find. So the whole goal is to find D. I totally did that wrong though. Right? What did I do here? I did opposite of hypotenuse. That's not right. Sorry about that. Get caught up looking at other things. Let's try that again. Cosine of theta is going to equal adjacent over hypotenuse, which is the magnitude of PS. So if I'm trying to find this distance here, that distance is going to equal the magnitude of PS times cosine of theta. And then of course, I need the magnitude of the other vector because I want to make one of my formulas show up. So I'm going to write this as the magnitude of n times the magnitude of PS times cosine theta divided by the magnitude of n. This top part is the dot product of those two vectors. So this is equal to the dot product of n and the vector PS. And then we take the absolute value of it because our distance should be positive, divided by the magnitude of it. So that's how we're going to calculate this. Okay, now we should actually fill in the things. So we might like to know what our vectors are. So we know what the vector n is. N is still, where'd you go, n? You're hiding from me. It's right there. N is still 11, -2, 14. And the vector PS, well, if I'm going from P to S, it's going to be 1 - 4, -3 - 1, and -1 - 0. All right. So then we're going to just do the dot product of those. We're going to get 11 times -3 plus -2 times -4 plus 14 times -1 divided by, I should put absolute values around that. Divided by the magnitude of n, which is going to be the square root of 11 squared plus -2 squared plus 14 squared. So let's see what we get. So that's going to equal, let's see, absolute value of -33 plus 8 minus 14 divided by the square root of 121 plus 4 plus 196. So we end up with, okay, -33 plus 8 is -25 minus 14 is the absolute value of -39 divided by the square root of 321. Gross. So we get 39 over the square root of 321. That's how far apart those are. Let's see. Can we change the notation of point S for clarity with the S and L2? Oh, yeah, that's a good point. Yeah, fair enough. Well, I mean, it's too late now, but yes, in general, you could totally change that. I would say, although it's not super obvious, that I am using a capital S here and a capital P here, and this is a lowercase s, but I agree. You could totally use a different letter because that might make things a little more clear. The other thing, someone asked, where did the points P and S come from? So the labels came from just, those are typical labels. The actual points came from setting in L1. So this is my plane 1. This is my plane 2. The point here, 1, -3, -1 came from this line being in this plane and setting t equal to 0. So I got 1 minus 3 minus 1. And similarly, in this plane here, I took a point on the line L2 by setting s equal to 0 and getting 4, +1, 0. You could totally pick other points, right? You could definitely do this with other points by letting t and s equal like any other values you wanted. But usually we pick the path of least resistance and pick values where they're both 0 because it's just easier. Good questions. Other questions? So I should reemphasize, when you're finding distances between things, it's almost always a situation of drawing a triangle in some way. Can you show the answer again? Definitely. Right, let me show the answer with the picture, just so you can see kind of both together. Yeah. Hopefully that's helpful. Other questions? I'm trying to think of other questions I would ask. Yeah.
I'm sure you mentioned this, but what happened to the cosine?
Yes. So the whole idea, whenever you're trying to find distance between two things, is you're almost always 1, drawing a triangle, 2, using a trig function, either sine or cosine. And so the idea here is that the reason we're trying to use sine or cosine is because sine or cosine are part of formulas for either the dot or the cross product. So what we're using here is the fact that in general, if you take u dotted with v, it's equal to the magnitude of u times the magnitude of v times cosine of theta. So what's happening is we're transforming this into this. Oh, sorry, you can't see the things I'm writing. Apologies. Right. So the whole idea is we're taking our magnitude of n times magnitude of ps times cosine of the angle between them and replacing that with the dot product of n and ps.
Okay.
In a similar way, in the previous problem, you can also say that u cross v, I should say, really the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times sine, apologies, times sine of the angle between them. Yeah.
So just have like that arrow over, and that's when you use a vector, and then you have the 2 lines. That's when you use the 5 vector.
Right. So the two lines around the vector n means the magnitude of n. Yeah. And sometimes people use one set of one line instead just because they're lazy. So someone might write this and they still mean the magnitude of v. They just don't want to write all the lines.
So you have to know that on the top, it's the absolute value.
So that's actually a really good question. How do I know that this has to be the absolute value without knowing it just is? Well, what kind of thing is n dot ps? Is it a vector or is it a number? It's a good question. So when you take the dot product of two vectors, what do you get? Do you get a vector back? No, you get a scalar back. And so I can't take, well, I mean, you can technically find the magnitude of a scalar, but we don't typically use that language. What we say is, oh, I'm taking the absolute, I know it's an absolute value here, because I'm finding the absolute value of the number I'm getting. Whereas if I wrote that and it was around a vector, I know I'd be finding the magnitude. So like when I write this, I know it's a magnitude because the thing that's in there is a vector. So I know it's not great that people don't use the same notation all the time, but it is a reality that people go back and forth between notations that are convenient for them. Let's see, there's some questions here too. So skew is when the values don't match for Z1 and Z2. Yes, that's correct. If you're trying to find, well, first of all, I should say, if you know the lines aren't parallel, and then you find that they don't intersect because the Z values aren't the same, then yes, they end up being skew. Will the distance formula always be the same for these problems? No, they will not. And yeah, so the distance formula, so really there's two formulas. I don't remember them at all. Like I could not tell you if you ask me like, James, your life is on the line. Can you tell me the distance formula between two planes or a point in a plane or a point in a line? I would say, hell no, I need to draw a picture. So I always have to draw a picture to figure out what's going on. You can memorize formulas. They are certainly in the book. And you might want to do that, but it's not what works for me. So definitely, yeah, in fact. So, right, if you look back at what we did, so I'm just gonna go back to what we did last time. So previously, we looked at the distance between this point, this point and this line, and we ended up dropping a perpendicular from that point to the line, finding another point on the line, and then doing the usual thing, drawing an angle using trigonometry. I'm trying to find this distance, so I ended up using sine, because sine of that angle equals that side over that side. So in this instance, we ended up using the cross product because we got to this formula here, and then we ended up replacing that magnitude of PS times the magnitude of V times sine of theta with the absolute value of their cross product. Now I say absolute value, really it's the magnitude of the cross product there, right? Because the cross product of two vectors is it's not a number actually. That's the dot. So the dot product always gives you a number. The cross product always gives you a vector. In fact, that's why if you look at some notes, it's called the cross vector product and the dot scalar product to let you know what you're getting out. The cross product or the cross of vector product always gives us a vector back perpendicular to the original two vectors. And the dot product always gives us a scalar back. Dot product is a number. Cross product is a vector.
And that's perpendicular. And the other one is scalar, so like parallel stuff.
No, there's not a really good interpretation. I mean, you could talk about how the dot product is kind of like, it's the product of the amounts of the vectors that are in the same direction, but it doesn't have as good as a physical interpretation. And so just to kind of go along, so you could memorize this formula if you wanted to for the distance between a point and a line, where PS is a vector from a point on the line to the point not on the line, and V is the vector that's in the direction of the line. I would draw a picture every time. And then I will also point out, just because we're reminding ourselves what's happening, if you want to find the distance from a point to a plane, this is the one where I said very strongly, make sure that when you do this, you don't drop a perpendicular from your point to the plane, even though you want to so badly. Right? You don't want to draw perpendicular. You want to draw your vector from your point on the plane to your point that's not on the plane, and then also your normal vector shooting out of that point. Yeah. And then you draw the angle, you think about what you want. Oh, I want this distance here. So then you do all the things. You say, oh, cosine is that side over that side. And then you go back and you find what your distance is. Your distance is that times that. You throw in the length of the vector you want again, so that this top part becomes now the dot product. And then here's your formula. The distance between a point and a plane is the absolute value of the dot product of PS dot n divided by the magnitude of n. You could memorize this formula. I don't think you should. That's not true. I think you should if that works for you, right? If memorizing formulas like totally works for you, you should do that. It does not work for me. I would need to draw this picture every time. Now that might not be very efficient on an exam. You might actually need to memorize these things. So take my words with a grain of salt, right? You can do it. There's many different ways to do it. I am not good at memorizing these formulas because I'm like, oh, which one do you dot with n and which one do you cross product with n? Right? I wouldn't have an easy time remembering that. And then, yeah, this one also, same sort of thing. This one, we really are kind of doing the same-ish work we just did before, where we're finding the distance from a plane to a point on the other plane, right? That's what we're doing. Do we said to find the point on the other plane first, kind of? I guess no. Those are your three distance formulas. And kind of really the last two are the same. They're both the magnitude of the dot product, or the absolute value of the dot product divided by the magnitude of the normal vector. I would still draw the pictures each time. It just, I feel like what works better. Other questions? You guys are asking good questions, and I'm happy to like address them. I think we'll do a little more practice after this. I mean, honestly, the best way to learn this is to practice it on your own, to actually draw the pictures, to do the things. That is how we're going to do it. Let's talk about two other things we can do with these ideas of 3D stuff. Well, yeah, actually, let's do it. So let's say we wanted to find the angle between two planes, specifically the planes x plus 2y plus 3z equal to 6. We'll call that plane 1. And at x minus 2y plus 4z equal to 8. We'll call that P2. All right, so here's the idea. We've got two planes and they're doing, I'm going to try and draw them. So yeah, that's all right. Sure. So here are our two planes, plane 2 and plane 1. And there's some angle between them. Actually, I should point out there's actually two angles between them. There's unless they meet at a right angle. Thanks, yeah, I appreciate it. Someone said my picture was pretty. They're like, it's the first time. I really do. Thank you for the compliment. I appreciate it. So there's this acute angle right there, and there's this obtuse angle next to it, which I'm going to draw over here just because it's easier to draw and it won't be in the way of my picture. And we can find either angle. I would probably default to finding the acute angle just because that seems like the more pertinent piece of information, but whatever. So to do this, well, here's an interesting thing to think about. To find the angle between these two planes, we can actually find the angle between their perpendicular vectors. Because if you take a vector perpendicular to this plane and a vector perpendicular to this plane, the angle between them is still going to be the same. So if I draw the vector perpendicular to plane 2, which I'm going to call N2, and the vector perpendicular to plane 1, I'm going to call N1. Let's see. That, then the angle between those two vectors, the acute angle, is the same as that acute angle there, right? I've taken, this angle here, sorry, that angle there, and just rotated it 90 degrees. So now it's that angle there. Sorry, I'm rotating the paper instead of the picture. So finding the angle between two planes actually becomes pretty straightforward because all we have to do is find the angle between the two normal vectors. Okay. How do we find the normal vectors? What is, in fact, so I want you all to write down on your own. It's an easy question if you remember anyone, it's not even a trick if you just remember what it is. So write down the vector n1 and n2, the vectors n1 and n2. They are practically on the page already. Some water. Yeah, 15 more seconds. Thank you. Yes, that is correct in the chat. So the vector for n1, oh, sorry, yeah, 5 more seconds. So n1 is the vector 1, 2, 3. N2 is the vector 1, -2, 4. Cool. Anyone? Right, we talked about this before. The vectors perpendicular to planes, you just get the components from the coefficients of x, y, and z. So then if I want to find the angle between them, I know that okay, fine. So if I want to find the angle between n1 and n2, I know that n1 dotted with n2 is equal to the magnitude of n1 times the magnitude of n2 times cosine of the angle between them. So if I want cosine of the angle, it's going to be n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. Which is going to be, so let's see, n1 dot n2 is going to equal 1 plus -4 plus 12, right? 1 times 1, yep, divided by the magnitude of this, which is the square root of 1 plus 4 plus 9 times the square root of 1 plus 4 plus 16. 1 plus 4 plus 16 is 21. So we end up with cosine of theta equal to 13 minus 4 is 9 over the square root of 14 times 21, which is, I don't actually care, but it's 7 times 7 is 49 times 6. This is 14 times 21, 210. Now I'm like, I don't care, but I want to know 294, I believe. So then our angle theta would equal the inverse cosine of 9 over the square root of 294, which is approximately 58.3 degrees, or if you like radians, 1.018 radians. Okay, neat. So the angle between those two vectors is about 58 degrees, which means the angle between those two planes, I should say the acute angle between those two planes is about 58 degrees. And then the obtuse angle between those two planes would be about 180 minus 58.3, which is 121.7 degrees. So just said, theta 2 is approximately. Someone could ask for the obtuse angle versus the acute angle. I don't really know which way people prefer to phrase it. But there could be a reason to find one. Yeah. Oh, theta 2? So remember, so this angle here, theta 1 is the acute angle, and theta 2 is the obtuse angle. So they have to add it to 180 degrees. I don't think you would normally be asked to find theta, the obtuse angle, but if we wanted to, we could. Now, No, yeah, that's fine. Depending on how we did this, so it could have ended up that the two vectors we originally started with were at an obtuse angle. Like if we had happened to, like if this plane had been oriented differently, the two original vectors might have been not pointing at each other or pointing in an acute way, and then we would have had the inverse cosine of a negative number, which would have given us an obtuse angle, and then we would need to change it to acute if they're asking us for acute. How did I get that angle? I calculated it beforehand with the calculator, right? So yes, when you're trying to, so if I was doing this, if I was asked for the acute angle, I'd be like, well, without a calculator, that's as good as it gets. And then I need a calculator to get that. So let me ask you a question. Let's say I was doing this problem on a test and someone said, okay, tell me the acute angle between the two planes. And let's say we calculated it and we got to the point where we know that cosine of theta is equal to -2/3. And then, so if I was going to find theta, I would of course use inverse cosine. So I'd say theta is equal to the inverse cosine of -2/3. Now here's the problem. That angle is not acute. How do we know it's not acute? Well, inverse cosine of a negative number, or I should say cosine of theta, if cosine of theta is negative, what quadrant is theta in? Not in quadrant 1, quadrant almost, that's where sine is negative. 3 and 2. A cosine is the x value, so it's negative when x is negative. And specifically, it's in quadrant 2 because of the way inverse cosine is defined. So this angle is in quadrant 2. So to make it actually what we want is we would need to say, oh, really, I want 180 degrees minus the inverse cosine of -2/3. That's how you would change an obtuse angle that we didn't really know what it was. Like, I don't know what inverse cosine of -2/3 is. It's some angle bigger than 90 degrees and less than 100. That's all I know without using a calculator. But if I want to make it acute, I know I can subtract it from 180 to get an acute angle. Now, if we actually want to know what that is, if you're allowed to use a calculator, calculator time. Why is this backpack so impossible? So we could actually find, make sure you're in the right mode. You can't see that at all. It's funny, on the other class, you can kind of see it now. It's because of my looming present over here. Okay, so if you wanted to first check the mode, okay, I'm in degrees, cool. So then I would do the inverse cosine of -2/3. And oh, look, that the angle is definitely obtuse. It's 131 degrees. So then I would do 180 minus it. And then I get about 40 degrees. So if that's the way things were going and you had to have an acute angle, that's what you would do. You would subtract it from 180 if you knew it was going to be obtuse. One more thing, well, not one more thing, but the next thing, one more topic in this section, and then we can do more or we can move on. Let's find the equation of the line of intersection. For those planes. So still the same planes, x plus 2y plus 3z equal to 6, which we're calling plane 1, and x minus 2y plus 4z equal to 8, which we're calling plane 2. So, whoops, sorry. So I'm going to kind of draw my picture again, although not as much of it really. So there's the line of intersection I want to know about. All right, so if I want to find the line of intersection, well, to find the line, I need two things. So just like in 2 dimensions, I need two things. I need a point and a slope. in 3 dimensions, I need a point and a direction instead of slope, right? Direction is the analog for slope here. So I need 1, a point, and 2, a direction vector. Well, the direction vector is actually not hard at all. Because here's what's kind of cool. This line, well, I should say, this vector that is normal to the second plane, P2, and this vector that is normal to the first plane, P1. If I'm a vector that's perpendicular to a plane, I am perpendicular to every line in that plane. So if this is perpendicular to this plane here, it's definitely perpendicular to the line L. And similarly, if this vector is perpendicular to the plane P1, it's definitely perpendicular to the line L that's contained in it. So once again, I see a line, a vector, that's perpendicular to 2 other vectors that I want to find. Or I should say, I want to find the vector that's on the line. Well, if I have 2 vectors perpendicular to it, I'm going to take their cross product. So to find the vector, in the direction of the line L, all we need is N1 cross N2. Always works. So if you have 2 planes that intersect, you can just cross product their normal vectors and you'll get a vector that is in the direction of the line where they intersect. So that's going to be, let's see, I, J, K, and 1 is 1, 2, 3, and 2 is 1, -2, 4. I feel like we do this calculation enough. You should get good at doing it kind of without writing it all. So you can definitely write it all out, but I can also see it's going to be, okay, the first component is going to be 8 minus 6, 14. Second component is going to be minus 4 minus 3. 4 minus 3 is 1, so it's a -1. And the last component is going to be -2 minus 2. You could also write it out, right? It's totally fine to write it out. If you don't want to just do it like this, you'd be like, oh yeah, it's I times this minus J times this plus K times this. But if you want to practice doing it, you can get faster at it. And then we also need a point. So a point. So how do we find a point? Well, it's possible. Oh no, is it possible? Let's see. So yeah, so let's make the assumption that this line probably goes to the XY plane. It might not. Maybe this line is parallel to the XY plane. It's not, but it could be. And if it's not parallel to the XY plane, then it's definitely going to cross the XY plane and can have a component where Z is equal to 0. So what I'm going to do is I'm going to set Z equal to 0 and then find some points where we can solve for X and Y. So I set Z equal to 0. I'm going to say, okay, X plus 2Y equals 6 and X minus 2Y equals 8. Great, I can solve both. I can really just add those together, or I can solve for 1 either way. So if I add X minus 2Y equal to 8, I get 2X equal to 14. So I get X equal to 7. Plug that back in either one of these places and get, sorry, not there, there. And get 7 minus 2Y equal to 8. So negative 2Y equals 1. So Y equals -1/2. And then we can solve for Z, and then Z equals 0. So our point is 7, -1/2, 0. This is definitely not the only point, right? There are probably literally an infinite number of choices. You could have set X equal to 0 and then solved for Y and Z and then gotten another point that way. So here's what we have. Our point is 7, -1/2, 0. Our vector is, where'd it go? 14, -1, -4. So the equation of our line, 1 second, I'll definitely answer that. The equation of our line is 14, x equal to 14 plus 17. Oops, I got it backwards, sorry. Trying to squeeze it in here, I got it. The equation of our line is 7 plus 14t is what x is equal to. Y is equal to -1/2 minus 1 times t. And z is equal to 0 minus 4 times t. A point in our direction. Sorry, that's a little squeezed in there. So why is it set to 0? So basically so that we can find a point. I'm, again, making the assumption, which is not incorrect, but I'm kind of just guessing, saying, well, that line probably goes through the XY plane. It might not, or maybe I happened to get a line that was parallel to the XY plane. If that happened, then I would let one of the other ones be 0. Because you can't be parallel to all the, well, no, you can't be parallel to all the planes. So you can definitely be parallel to 2 of them, like XY plane, XZ plane, but then your line would be like, then your line would be like x equal to a number. So, right, you can't be parallel to all the planes. So set one of them equal to 0. If it doesn't work, then try a different one. So just for example, just to kind of quell your fears, if there are fears, if instead I had said, let's let y equal 0, okay, then I have x plus 3z equal to 6, and I have x plus 4z equal to 8. And then I subtract those from each other because that seems easy. I get 3z minus 4z equal to 6 minus 8. So z equals 2. And then solving for x, x plus 6 equals 6. Oh, I get x equal to 0. That's interesting. And then I also get y equal to 0. So I also could have written this equation instead of, so one was writing the line as x equal to 7 plus 14t. Wow, can I write t's? Y equal to -1/2 minus t, and z equal to -4t. But another way of also writing the line could be x equal to 0 plus 14t, y equal to 0 plus, what's the y value? -t. And z equal to 2 minus 4t. Both of these are the same line, they just start at different places. And you can kind of see here, if I set, no, it's actually easier to see here. Here, if I set t equal to -1/2, I get the initial point here, right? If I set t equal to -1/2, I get 7 minus 7, which is 0. And I get -1/2 minus -1/2, which is 0. And I get -4 times -1/2, which is +2. So here, t equal to -1/2 is equivalent to here, t equaling 0. You can make the assumption on a test. I don't think you have to prove it. Yes, vector form would also be fine. So you could totally write this as, I never like to write it. I never write it as a vector, but yeah, you could totally write it as like x, y, z equals the point 0, 0, 2 plus t times 14, -1, -4. That would also be perfectly legitimate. Yeah. And yeah, either x, y, or z can be set to 0. So here's what will happen. Let's say you happen to have one where it didn't work. So let's say you set x equal to 0 and you couldn't solve for y or for z. Like you got to a point where you're getting something like, I'm trying to think of now, like what you're gonna end up with, like 3 equal to 2. Right? If you pick a point that doesn't work, you're gonna get some nonsense equation at the end where two things there can't be equal or equal to each other. Then you just start over and pick a different one. And eventually one of them will work. And usually the first one you pick will work because usually your things aren't parallel in weird ways. But yeah, you don't have to prove it. It's just, we're just trying to find a point. Because I could definitely go back and be like, well, yeah, of course, this point I found the point 0, 0, 2. For sure, that's on both of these planes. Let's check. If I plug in 0, 0, 2, check. If I plug in 0, 0, 2, check. It works. So you don't have, I mean, that could be your proof if you felt like you needed to show that it was actually on it, but I don't think you need to. Other questions? Okay, so here's my question. Should we do more practice with this, or should we start talking about vector valued functions? Chapter 13 stuff. Who votes for more practice? Who doesn't want to vote?
Can we do like the chapter 13 and give time for that?
Sure, yeah, that's good. Yeah, let's see, chapter 13 stuff. All right. Yeah. This stuff is always kind of funky. Sure, yeah. Let's start there. All right, sure. So a lot of this vector value stuff is kind of helping us set up what we're going to be doing in 21D. So let's look at an example here. Let's find a vector function for the intersection of these two curves, x squared plus y squared equal to 4 and z equal to x squared. So in 3 dimensions, x squared plus y squared equal to 4 is a cylinder, right? It's a circle where you have no restriction on the z value. So you have something that does kind of like this. All right, I could draw like a coordinate system here. And then z equal to x squared, well, that's a parabola, but it's a parabola. It's not, so really, it's also a cylinder. It's a parabolic cylinder. So we call something we extend in some direction. And it's going to look kind of like, sure. Yeah, I can try. I can do that. So here is our z equal to x squared. And so if we're going to see where these intersect each other, again, this is where my drawing skills, I could probably make this happen. Let's see. So, sorry, apologies. I'm trying to draw this so it actually looks nice. So give me just a second here. Over here, if y is 2. Okay, so we're kind of getting that. Yeah, let's do it like that. So we're kind of going to get there, and there, and then this direction. We kind of like, sorry, it's always hard to draw the things. Yeah, it's kind of it's. Okay, it's not terrible. It's supposed to kind of look like a Pringle. That's what this surface should look like, is like a Pringle. And so what we're trying to describe, the curve we are looking at, the curve is the edge of the Pringle. Let's go for some Pringles. Like Pringles. Sour cream and onion, please. No other Pringles. This is a sour cream and onion Pringle. This is not a regular Pringle. I know they look weird. No, sour cream and onion just tastes better. Or whatever you like. I'm not biased against other Pringles. I will eat any Pringle. So we're trying to describe the coordinate of a point at any moment. So like at time equals 0, the point's right there. And then, 1 second later, it's right there. And then another second later, It's right there. And so we're trying to kind of figure out a way of describing where this point is at any particular time t. So typically this means parameterizing things. Right? We want to describe the points on this curve in terms of some parameter, usually t, although you can use other things. Theta is also often a good parameter to use if things are looking. In fact, theta might be a good choice here, but we're going to use t. So we're going to rewrite both of these. Since we know we're on a circle, it probably makes sense to say, well, on this circle, you could say that x equals 2 cosine of t and y is equal to 2 sine of t. It's totally true. In fact, if you know you're on a circle, it is often a good idea to make that internal connection right away. Oh, if my circle's radius 3 sine of the origin, x is 3 cosine, y is 3 sine. It doesn't have to be x equal to cosine, y equal to sine, but it often, works best that way. But it would totally also work to say x equals 2 sine of t and y equals 2 cosine of t. And the reason it works is because, well, if you throw those into that formula there, it's always true. It's definitely true that 2 cosine t squared plus 2 sine t squared, that's equal to 4 cosine squared t plus 4 sine squared t. That's equal to 4 times cosine squared t plus sine squared t, but cosine squared plus sine squared is always equal to 1. So it definitely satisfies this equation. T can be anything. And x being 2 cosine t and y being 2 sine t will always make this equation work. So then we know what x is in terms of t, we know what y is in terms of t, and we know what z is in terms of x. So we can say, well, now I'm going to substitute in what my parameter for x is. So z is x squared. Yeah. Sorry, you can't see. Yeah.
So we could choose 2 because it was 4.
Yes.
Choose any number depending on.
No, I specifically had to choose 2 because it's the square root of 4.
So if it was we would choose 3.
Correct. Yeah. So if you have more generally, just here, right? If you have the circle, x squared plus y squared equal to r squared, you can always make the choice that x equals r cosine t, y equals r sine t. Always going to work. And you can probably even usually switch them. We just don't. So then our z is going to equal 4 cosine squared t. And so what that means is we can write our vector valued function r as a vector as a function of t is the vector, well, the x coordinate is 2 cosine t, the y coordinate is 2 sine t, and the z coordinate is 4 cosine squared t. So this gives you the position on the curve in 3 dimensions at time t. So for example, I've got some room here. Yeah. Sorry, I'm covering up whatever my stuff here. So just to find a few points. So we can say that r of 0, so time equals 0, I'm going to get, well, cosine of 0 is 1, sine of 0 is 0. So I'm going to get the point 2 times 1 plus 0. Sorry, not plus. 2, comma 0, comma 4. So I'm getting the point 2, 0, 4 right there. And then say at pi over 2, well, cosine of pi over 2 is 0. So I'm going to get the point 0, 4, sorry, not 4, 0, 2, 0, which would be like the point like right over here. So the XY plane should be like at this height here. Sorry, I kind of drew it backwards. Just trying to make it easy to draw. So that's where the next point is, or the next point I've chosen to look at is. And you can see, right, if you plug in pi, you're going to get this point back here. So you should check for yourselves. If I plug in pi, you should get the point -2, 0, 4. Kind of neat. More than neat. useful. So, yes. What we're going to do is for each vector function, we can determine the following. Where we begin, the direction of travel, clockwise or counterclockwise, speed, acceleration. Okay, so let's look at something, what we were just thinking before. So let's say we are now just looking in 2 dimensions for a minute. So for example, let's say we're looking at the same circle, x squared plus y squared equal to 4, which we're going to write as x equal to cosine of 2t, sorry, 2 cosine of t, and y equal to 2 sine of t. And if I want to write that as a vector value function, I'm going to write r as a function of t is the vector 2 cosine of t, 2 sine of t. And you can use this notation, or you could use the ij notation. You can say 2 cosine of t I plus 2 sine of t j. Either way is fine. So let's find where we begin. Well, the beginning is easy. We begin, well, I should say, it's easy if you're given kind of, so typically without any other thing being said, we're going to be in at t equals 0. Maybe they're going to tell you that the domain is something else though, but without any other kind of information, we're going to begin at t equals 0, which is going to give us r of 0 equal to the point 2 comma 0. So graphically, we're on the circle of radius 2. And we're beginning here. Okay. So now, what's our direction of travel? Are we going clockwise or counterclockwise? Well, to really tell, I'm just going to plug in another point. I could plug in, and I should say, the direction of travel is always under the assumption of as time moves forward. So as time goes on, are we going to travel in the clockwise or the counterclockwise direction? So I would just pick the next easy value of t to plug in. You could pick either pi over 6 or pi over 4 or pi over 2, whatever makes the most sense for you. I'm going to pick pi over 2. So if I pick pi over 2, I get 2 cosine of pi over 2 and 2 sine of pi over 2, which is 2. So I'm going to move to up here. So it looks like I'm traveling in the counterclockwise direction. If you wanted to check a few more values, like you could check pi over 6, pi over 4, pi over 3 to see that, oh yeah, we are really moving in that direction. But I don't think we need to. Okay, what about velocity? Well, I said speed, but then I said velocity. They're not the same. Speed is a magnitude or a scalar. Velocity is a vector. So speed is the magnitude of velocity. So if I'm going to find speed, I need to find the magnitude of the velocity vector. Now, fortunately, the velocity vector is exactly what you think it is. Just like in regular non-vectory math, velocity is the derivative of position. So here, the velocity vector is the derivative of the position vector. So it's the derivative of r of t, which is going to be, well, let's see, the derivative of 2 cosine t is -2, oh, I see why that's okay. -2 sine of t, and the derivative of 2 sine of t is 2 cosine of t. Now, it's not very exciting in this particular example because the magnitude of this is just going to be 1. The magnitude of velocity here is the square root of -2 sine. Oh, no, it's not going to be 1. I apologize. Not 1. It's going to be a little more exciting. It's going to be the magnitude of this is going to be that component squared plus that component squared. Again, I'm seeing a sine squared plus cosine squared, but there is a multiple of 4 in there. So it's going to be the square root of 4 times sine squared plus 4 times cosine squared, which is going to be 4 times the square root of sine squared plus cosine squared. Sorry, the square root of 4 times sine squared plus cosine squared. That's a 1. Square root of 4 times 1 is the square root of 4, which is 2. So our speed is a constant speed of 2. 2 what's? 2 whatever's per whatever, right? Nobody said anything about units here, right? We could give ourselves units if we wanted to, but we don't really need to. If you said this circle had a radius of 2 meters and it was moving to this position at t seconds, then you can say the velocity was in meters per second. And then what about acceleration? Well, just like in regular math, regular physics, acceleration is the derivative of velocity. So the acceleration vector is the derivative of the velocity vector, which is equal to, let's see, derivative of -2 sine t is -2 cosine t, and the derivative of 2 cosine t is -2 sine t. And something worth noticing, because it happens a lot. So question, is the acceleration vector perpendicular to the velocity vector? So if anyone's ever asking you to check if two things are perpendicular, what they're asking you to do is to look at their dot product and see if it's 0. Well, let's check. Let's check A dot V. Okay, I've got both of those. There's A, there's V. So that's going to be A, which is -2 cosine t, -2 sine t, dotted with V, which is -2 sine t, 2 cosine t. And yeah, I think we can see that it's going to be 0. So I'm going to get -2 cosine times -2 sine. So that's going to be +4 cosine t times sine t, plus -2 sine times 2 cosine, which is going to be -4 sine t cosine t. And 4 cosine times sine -4 sine times cosine, that's going to be 0, no matter what t is.